All right, good morning, everyone. Morning after replay. I'm glad to see a semi-full house here. My name's Leif Reinert. I'm a senior product manager at AWS on our EC2 accelerated computing team. So our team owns our hardware accelerated EC2 instances. These are instances powered by GPUs and FPGAs and specialized hardware accelerators. And today I'm joined by my technical counterpart, Amr, to talk to you about AWS ML infrastructure services and some of our most recent launches and offerings in this space. So jumping right in, one of the key insights that we've gathered from talking to customers over the past few years about machine learning is that the reach of ML is really growing drastically. Where ML was once kind of a research-driven technology that was dominated by a few key large tech companies, now we're seeing customers across industries and adopting ML as a core part of their business and using it to differentiate themselves within their industry. So this is customers in automotive and in transportation and retail and healthcare and manufacturing are coming to AWS to look for these AWS ML infrastructure services and help solve their ML challenges. And with that expansion in application space and different customers adopting ML, we've seen a rapid increase as well in the types of models customers are training. So where just 5 years ago, customers were training models on the order of 50 to 100 million parameters, we're now seeing customers training models on the order of 175 billion parameters and greater. And with that comes increased complexity and increased costs. So as customers are productionalizing these models, training them, deploying them for inference, applying software optimizations on top of this model infrastructure, their costs are going up drastically, and they're coming to us and asking, how can we help solve this complexity and this cost challenge? And at AWS, we're really taking kind of a three-tiered approach. First, we're continually working to provide the broadest and deepest set of AI and ML services and infrastructure in the cloud. And so this goes from our self-managed ML infrastructure, if you're using EC2 and building up your ML infrastructure on your own, all the way to pay-as-you-go API-driven services, leveraging some of the research from our AI research team at AWS. And as we are developing this portfolio of AI and ML services, we're continually working to push the bar further on price performance. So looking to lower the cost to train for customers, lower your cost per inference. And this can come from our new infrastructure we're launching, so maybe new accelerators or accelerators we're designing, or new pricing structures or new software optimizations that allow you to more efficiently use that infrastructure. And then finally, we know that while the ML infrastructure is important and your compute is important, that customers are building comprehensive solutions on the AWS cloud. So you also need storage and database and security and analytics services to complement those AI and ML infrastructure and build an end-to-end solution. And this approach really resonates with our customers. We've got thousands and tens of thousands of customers building their AI and ML applications on AWS. More machine learning is happening on AWS than anywhere else in the cloud. These are customers like Capital One and Korean Air and Pinterest and the NFL and Formula One. These customers are coming to AWS to help solve their ML challenges. And so with that backdrop, we've talked about kind of what are the challenges customers are facing, why are they coming to AWS for these solutions. We want to dive a little deeper into what these solutions are and kind of what tools specifically our customers are using. So this is kind of the infamous AWS ML stack. You may have seen this slide before, but this is constantly growing set of services. The bottom layer, we've got our frameworks and infrastructure. So you've got EC2 instances or compute that leverages accelerators like GPUs, hardware accelerators, designed for machine learning and high-speed network interfaces. We combine that with framework services or framework optimizations from our ML frameworks team that optimize the performance of these key ML frameworks on AWS. So for TensorFlow and PyTorch and the other key frameworks customers are using, they're able to use these frameworks on AWS and leverage those optimizations through things like deep learning AMIs and deep learning containers that come prepackaged with all the frameworks and SDKs you need. Moving up a layer, we've got Amazon SageMaker. So we talk to customers that like to build their own ML infrastructure from the ground up with that bottom layer, but we also talk to customers that really just want to focus on the data science, and they want to build their ML application, they want to train their models and deploy their models, and have AWS manage that underlying infrastructure for them. And that's where Amazon SageMaker is a great service, and it provides an easy-to-use interface for just that, building, preparing your data, building your model, training your model, and deploying it in the cloud. And then in that top layer, we've got AI services. So AI services, in this case, this is leveraging, like I mentioned earlier, a lot of the research that our AWS teams have done, pre-trained models that you can use for applications like vision and speech and search and kind of access as a pay-as-you-go manner and integrate into your application with a few simple API calls. So today we're really going to actually focus on this bottom layer and the ML frameworks and infrastructure. And we're really going to dive into each kind of infrastructure offering, each EC2 offering, and some of the key additive offerings on top of those EC2 infrastructure that allows customers to be successful and build really functional ML applications. And first, we'll start with training. So for ML training, we've got a broad portfolio of GPU instances as well as custom ML accelerator instances to solve different ranges of ML training problems, whether it's really large-scale distributed training or kind of more medium-scale or smaller-scale training. We've got an infrastructure solution that can meet that need. And we'll start with P4D. And so P4D is a recently launched GPU instances. These are powered by NVIDIA A100 GPUs and are really one of the most powerful GPU instances in the cloud. They offer 2.5 times higher performance than our previous generation P3 instances, which use NVIDIA V100 GPUs, 4 times the local storage, 25% more GPU memory, and 4 times higher network bandwidth as customers are building those larger and larger clusters of ML training applications. So we offer P4D in one size at P4D 24x large with those 8 A100 GPUs, 600 gigabytes per second GPU interconnect within the box with NVSwitch, 8 terabytes of NVMe, and then that 400 gigabits per second EFA plus GPU direct RDMA. And what this is important for is really scaling out and having that GPU or that internode communication. And we use technologies like EFA and GPU direct RDMA to make that communication as efficient as possible. And so as customers are building out these large clusters using these technologies, we knew that it wasn't just enough to say we're going to build an instance type or build a server that uses these GPUs and has this networking, but we really needed to think about it at the data center level as well. And that's when we introduced EC2 Ultra Clusters. And EC2 Ultra Clusters use over 4,000 A100 GPUs, leveraging a fully non-blocking petabit scale network infrastructure and pairing that with high throughput, low latency storage solutions with Amazon FSx for Lustre. And so in the diagram here, you can see we've got our clusters of GPU instances with P4D. You've got hundreds of these P4Ds all under a non-blocking network fabric, and they're communicating actually bypassing CPU through GPU direct RDMA. And this is what gives customers really efficient scaling out to hundreds of nodes. And then with FSx and that high throughput, low latency storage, you're able to keep all of these P4D instances saturated with data as you're training your model. So diving a little bit deeper into each of these pieces, EFA is, like I mentioned, that ultra low latency elastic fabric adapter, or it's an AWS design network interface for inter-instance communication. It's best for those tightly coupled ML and HPC workloads, so using those libraries like MPI and Nickel. And in the case of P4D, offers up to 400 gigabits per second of network bandwidth with those less than 15 microsecond network latencies, and it achieves that through a number of techniques like out-of-order transmission and packet spraying. And I imagine we can dive into some of those details later in Q&A if you like. And then the other piece there was FSx for Lustre. FSx for Lustre is a scalable file system. So as you're adding more storage, your performance is increasing, and you get sub-millisecond latencies, terabytes per second of throughput with millions of IOPS on FSx for Lustre. You can configure it really to meet your needs, so you don't necessarily, it's not just one size fits all here. You can use different types of storage mediums to meet the speed at which you need to access your data, and then also keep your data synchronized through your other data sources, whether it's a data lake out in S3, you can keep that synchronized with FSx for Lustre as well. So putting these pieces together, you've got P4D instances and EC2 Ultra clusters and EFA and Amazon FSx for Lustre. We wanted to show some benchmarks in how our ML team was able to leverage these pieces to really achieve a high performance on some of the most popular machine learning models. So in this case, we set out to train GPT-3, which is an autoregressive language model at 175 billion parameters using 120 nodes of P4D, 960 of these A100 GPUs in one really large cluster. We were able to achieve 26.5 sequences per second for that model. In order to do that, we also used techniques from our SageMaker and ML Frameworks team, and they provide a set of libraries called SageMaker Data Parallelism and SageMaker Model Parallelism that allowed us to partition that model efficiently, pipeline that execution, and reduce that overall time to train. And so while this is a benchmark that stands alone, we also want to make sure we're sharing these customer stories here as well. RadAI is a customer really in the radiology space, and they use machine learning for radiology services and to help streamline radiology reporting. And they found that with P4D instances in these ultra clusters, they're able to train their models almost 2.5 times faster with higher accuracy in these previous generation GPU instances. And what this gave them, what this ends up being is higher quality care for customers across the US, more accurate predictions, more accurate reporting. So next, we wanted to talk about Trainium, and this is one of the more talked about launches this year. Trainium is a custom chip built by our Annapurna team, and the second chip built by the second ML ASIC in AWS, and this time we're focusing on training. Trainium instances provide 60% higher accelerator memory than P4D, 2 times the network bandwidth, so actually going to 800 gigabits per second with Trainium. And we'll also deploy these in ultra clusters. It's just in preview now, but it'll GA later this year. But you'll be able to scale to hundreds of nodes with Trainium as well. And we'll offer these 2 instance sizes on Trainium at 2x large and 32x large. So that 2x large size is great for early experimentation and micro benchmarking, where 32x large you can use to actually scale out and train these larger models. Trainium will use what's called the Neuron SDK, same as what was used in our Inferentia chip, and we'll cover Inferentia in a bit as well. But the Neuron SDK is integrated with TensorFlow and PyTorch, so customers operating at that framework level can continue using the same workflows they use today. For Trainium, although it's early days, we're just in preview now, we also wanted to highlight a quote here. And Anthropic's a customer that's really operating at the cutting edge of machine learning now, setting out to train very large models. And they were excited about Trainium because it's going to help them iterate faster, retrain their models more frequently, and keep their costs under control. And so we talked about GPUs, and we talked about our own chips, but we know that there's also compelling vendor options out there. So at AWS, we're going to continue to launch the highest performing GPU instances. We're going to continue to innovate on our own silicon. But in this case, we also decided to partner with the Habana team, it's an Intel company, to launch DL1 instances, which feature up to 8 Gaudi accelerators by Habana Labs. And these are also purpose-built for deep learning training. They offer up to 40% better price performance than our current generation GPU instances. They use what's called the Synapse AI SDK, and is also integrated with TensorFlow and PyTorch. And so this is another cost-efficient option. And what we've seen from talking to customers is that there's different software stacks. Customers may prefer to use Neuron. They may prefer to use Synapse. They may prefer to stick with the CUDA and CUDNN NVIDIA environments. But having that selection really allows customers to right-size, right-size their model and their application to meet their needs there. So DL1 instances coming in one size with 8 Gaudi accelerators, 256 gigabytes of accelerator memory, 4 terabytes of NVMe, and that 400 gigabits per second of networking throughput as well. For DL1, we partnered with Seagate, or we worked with Seagate, and they were able to see the benefit of DL1 and the price performance advantage of DL1 for their application in hard drive defect detection. So using kind of this computer vision application in DL1 instances, they were able to see that price performance benefit at up to 40% better. Now diving into ML inference, so we talked about the training side. Inference, when we're actually deploying these models, we offer a similar story. We've got GPU instances that offer higher ML, that are pushing the bar further on ML inference performance, but we also are looking at that cost efficiency as well with our own ML ASICs. So we'd like to start with Inferentia here. So Inferentia we launched, I guess, a couple years ago now, and it's our first ML chip designed by Amazon. It's the lowest cost in the cloud for deep learning inference, so up to 70% lower cost than our GPU instances. Also having that seamless software integration, we offer multiple sizes with Inferentia, so you can kind of right size your model to actually deploy it. And with Inferentia, we wanted to highlight the use case of Airbnb. Airbnb has millions of hosts and guests around the world, and they had an NLP application where they're building chatbots and making sure their customer support platform has an intelligent response and can scale. And so they were using specifically a PyTorch-based BERT language model, and they saw 2 times performance improvement out of the box by testing out Inferentia. So not needing to make a lot of code changes, they're able to leverage this new ML ASIC and get going right away at seeing that cost performance improvement. And then the last instance we'll talk about here is G5. G5 was actually launched just a month ago and features up to 8 NVIDIA A10G GPUs with 24 gigabytes of GPU memory per GPU. And we think about G5 as really kind of our Swiss Army knife of GPU instances. We offer a large range of instance sizes from X large to 48X large. You can use G5 instances for training or inference. We really highlight them here in the inference section because we see this is where most customers will likely be using G5, but for smaller scale training, they can be great as well. And customers we've seen are using G5 for this broad range of applications. And so that covers our kind of instance portfolio for training and for inference. And what we wanted to close with here on kind of the instances themselves and how we're thinking about innovating on the infrastructure level is we started with our chips, and our Annapurna team continues to work and develop new silicon for training and for inference. We continue to work with our vendor partners NVIDIA and AMD and Intel to leverage the latest CPUs and deep learning accelerators. And then building those chips into the server, we're using the AWS Nitro system with AWS-built network adapters and storage adapters for high throughput and low latency communication across those interfaces, with up to 16 accelerators per instance or per server interconnected with those high-speed fabrics, offering up to 400 gigabits per second of network, and in the case of Trainium, at GA we'll offer that 800 gigabits per second of network, 80 gigabits per second of EBS, 20 gigabytes per second of local storage bandwidth. And then we're moving beyond the server level to actually the data center level. With EC2 Ultra clusters, we've got up to 4,000 GPUs in a single cluster. We'll have thousands of Trainium accelerators in single clusters, that petabit scale non-blocking network infrastructure that allows you to scale out seamlessly without oversubscription across many instances. And then finally, those MPI-style network interfaces, the AWS-built network transport protocol with EFA and GPU Direct RDMA, we're able to provide these really efficient ML training systems and then allow you to continue and deploy those for inference. So that covers the section of our slides. I'd like to invite next my colleague Amr up onto the stage to go into our ML Infra showcase and actually show a demo of some of this stuff in action. So I'll invite Amr up now. Thanks.
Okay, excellent. Just take a few minutes here to prepare the demo and the setup. Just make sure. Okay. Okay, so one of the things that Leif talked about was the EC2 Ultra clusters. And EC2 Ultra clusters is that layer that allows you to utilize high performance networking and to running to distributed training on AWS. One of the things that we can show here is our ability to actually utilize that in our services layer. So EC2 Ultra clusters is actually supported on our different AWS services such as ECS, EKS, and what we can show here in this demo is a 4-node P4D cluster running some example ML workloads using the EC2 Ultra clusters. So you can see here that we have an EKS cluster, 4 nodes. We're going to be training actually the Megatron 8 billion parameter model, a GPT-2 model. This was something that was a reasonably sized model that we could show within a respectable demo. Perhaps in the future we can do GPT-3 in future reInvents. But in this example we have here GPT-2. And I can show you here some of the mechanics that's involved with setting it up and how it's actually set up to actually run some of these platforms on EKS. So remember that an EC2 Ultra cluster is a combination of both the P4D instances as well as FSX. So within our EKS cluster, we actually have a persistent volume, group that's based off of FSX. So if I actually describe this persistent volume, we could see here that we've mounted a FSX using the CSI driver, and that uses a file system ID. This is the new file system with the new performance options that were announced a couple days ago, I believe on Wednesday during the FSX session. So this has the higher performance options that is mounted within our FSX cluster. So one of the things that we have within our cluster is our ability to handle a lot of that undifferentiated heavy lifting. And with that, what ends up happening is when you do set up the cluster, it automatically will set up EFA, it sets up GPU Direct, it sets up the networking layer for you. So by doing that, you can actually see, let me show what that looks like. It will actually set up the resources so that you can actually see the fact that it will install the NVIDIA GPU plugin for advertising the GPU devices into the pods, and also our 4 EFA ENIs. So remember on P4D, we have 4 EFA ENIs, each one's 100 gigabits per second, totaling 400 gigabits per second. So that's where that is exposed into our pods. Now, earlier I ran some of our benchmark tests. So one of them, for example, is our nickel tests. So if I take a look at the logs associated with our nickel tests, there we go. A couple of things here that we want to point out. So the nickel tests basically run different collective communication. So when you're doing distributed training, one of the efficiencies associated with nickel or the NVIDIA Collective Communication Library is the ability to take advantage of GPU Direct RDMA. Now, with this, we actually have the option of verifying a lot of the performance that we talked about, that Leif and I have talked about. For example, in our bus bandwidth for our nickel all-reduce, we get about 45 gigabytes per second of bus bandwidth. That's approximately 360 gigabits per second. So of the 400, this is what we're seeing when we actually run live. Another thing to confirm from a best practices perspective is when you do run these distributed training workflows, if you actually parse out the nickel log, and yes, it does look quite verbose when you take a look at it, one of the things that you can confirm is to see that the GPU Direct RDMA layer is actually being utilized when nickel calculates its distances between GPUs. Because what ends up happening here is when it actually sees what the nickel distances are for send and receive traffic between GPUs, it will actually expose what layer it's talking to. In this case, it's using EFA underneath the AWS libfabric layer with GPU Direct RDMA. So while that's going on, let me go ahead and submit our, I think I have the, okay, and let me, all right, so now if we take a look, we should actually see that starting to run. Yes, so that's in running state. So we're going to let that run for a while. It takes actually a few moments to warm up. While that's happening, I'll take you a tour through the code that's actually running. So the first one is our YAML spec for the actual job that I just submitted. So this file, the Megatron 8 billion parameter EFA example, this is using kubeflow MPI operator. You could use PyTorch operator or TensorFlow operator, but in this example, for this purpose of this demo, we're doing the direct MPI call itself. We're mounting our FSX file system where our data is located. And we also have a Docker image that we've prepared, which is actually available on ECR Public. If you wanted to, you can actually take a look at this. If you were to search or query this on ECR Public, you can actually download that exact container image. This is all available on GitHub as well. So if you wanted to test this out, this is also possible. Our data is mounted on this FSX path with our text document, checkpointing, as well as some metadata associated with setting up the environment on our cluster. The actual heart of the operation is right here with regard to the actual launch command. Now, this isn't quite verbose. This is just basically saying that we're going to be launching our training script across our cluster. In this case, the number of processes here actually matches the number of nodes, which is 4, because it's a four node cluster. In our worker side, we're also defining, as part of the kubeflow spec, some resources that we require. So each pod requires 8 GPUs and 4 EFA ENIs, mounting the FSX file system. Now, again, this isn't the part where, this is the launcher part, which is basically saying that we're going to be launching our PyTorch job across these four nodes. What actually is happening is when you call this script, the train 8 billion parameter GPT-2 model, this is where all the magic happens, so to speak, where we're actually defining what our environment is. This environment sets up some of the data paths, like I mentioned earlier. This sets up the multi-node parameter training for PyTorch when we do the distributed launch arguments for PyTorch. This actually sets up EFA. So these sets of environment variables, specifically the ones providing the provider to use RDMA, these specifically are actually all you would need to actually invoke GPU Direct RDMA, those 2 environment variables. And then after that is our actual Python PyTorch code. So for those that are familiar with Torch, you'll see that we are, with PyTorch, you see that we're actually using the Torch distributed launch, passing in our distributed args across our script to actually launch the GPT-2 training script. So now what we can do is take a look at the status of this. If we take a look at the logs for our launcher, yes, we can see that we're still actually in the process of compiling, but a lot of the same concepts that I mentioned here are actually happening here. We've confirmed that GPU Direct RDMA is actually being invoked, and we're actually resuming from a checkpoint that we've stored previously. So that's sort of the mechanics associated with the EC2 Ultra cluster and the ability to run that. Now again, this is on Elastic Kubernetes Service, which is unique for running it within Kubernetes and running it in a container context. It is supported on ECS or directly on EC2 or through parallel clusters. So all those are supported when we're running distributed training for the Ultra cluster. So we'll just let that go, and we will go ahead and show another quick example. I actually have just to keep things, my little cheat sheet when I want to log into for some of these commands. So we're going to turn our attention slightly to DL1, the Habana Gaudi instances. So with Habana Gaudi, again, we have DL1 24x large. These are 8 Habana Gaudi HPUs. We can actually confirm the 8 HPUs with the HL SMI command. And this will actually show us the 32 gigs of memory, our each individual HPUs that we can actually use. And in this example, we're going to go ahead and train a simple ResNet 50 model on the Gaudis. So this is all done through a container context. So what we'll do is we'll actually pull in a TensorFlow 2.6 Docker image, and we're going to yes, so now we're going to be inside of our Docker image here. Habana has full support for the container context. They actually have a container runtime, Habana container runtime, very similar to NVIDIA's container runtime, where you call the runtime and it will pass those devices into your container. If you run that same, I seem to have locked up. And this is where the demo fails. Yeah. Seems the networking has stopped. Give me one moment. Let me see if I can. Yeah. Networking. Here, let me turn off. There you go. Okay. Yep. All right, we're back. So what we'll do is we'll go ahead and git clone our model references, which is, again, available on GitHub through the Habana AI repo. We'll go into our ResNet Keras path. We'll set some environment variables for the Python path with extra libraries that are provided by Habana. And then we can start training. Okay, so we're going to let this continue training. So in a few minutes, after TensorFlow starts up, we can actually confirm some of the more recent performance gains. This is actually using our latest firmware for Habana 1.1, and there's actually been some performance gains. Once this actually starts up, we can see that. We should get around 13,000 images per second when this starts for across 8 Gaudi accelerators. So if we give this a moment, we'll let this run. Okay, so we've now started training our initial loop. Yeah, so now we could see here in one of our initial loops here, we're get, 13,100 images per second. So there's definitely some performance gains there. So that's just a quick example of just running across all 8 HPUs for ResNet 50 and what the latest performance numbers look like for that on the Habana Gaudis. So finally, one thing I want to end with in terms of the demo is from an ML infrastructure perspective is actually one important update that we've done recently. We've heard from customers that, while ML training is running, we want to be able to see live what our GPU metrics are while we're training in an ML context. So what we've done is we now have support through the CloudWatch agent to support monitoring GPU metrics natively. So once you install the CloudWatch agent into your AMIs and into your platform, you'll be able to actually see GPU metrics live. So in this case, we have that same EKS cluster that we were just working with in our P4D instances, and we can actually just populate all of them, and we can actually see utilization of the GPUs for our various instances in our EKS cluster. This shows basically our driver, the accelerator index, because the NVIDIA GPUs are indexed from 0 to 7, and our A100s with the instance type and our different metrics. We have about 6 metrics per index that measures both GPU utilization, memory utilization, the kernel, and some other key metrics. And all that is being pushed through CloudWatch. And again, that's all available through the CloudWatch agent. And there's a configuration file that you would set up that would allow you to take advantage of that. Yeah, so that was just a quick overview and a quick demo of many of the different offerings that we have within EC2 Ultra clusters, CloudWatch, and Habana Gaudi. So I'll switch it back and provide back to Leif. Thank you.
Okay. Great, thank you, Amr. So yeah, as Amr mentioned, that kind of shows our, from the cost efficiency with Habana to our largest scale ML infrastructure with EC2 Ultra clusters and GPU and our A100 GPUs. So thanks everyone for coming to the session. We'll dive into some Q&A. We'll actually hang around here for a bit after the session and be able to answer any questions you have on GPUs or hardware accelerators or building large clusters for ML training and inference. So thanks again for coming to the session. Hope you have a great reInvent.